So welcome to the lecture operating system overview. So today we are going to divide the lecture into two halves. In the first half, I will give you a very brief introduction to the definition of operating system and the different goals of an operating system, how it is important for running different programs and different type of operating system we have, and what are the basic features that goes to make up an operating system. So that will be covered in the first lecture. And in the second lecture, we'll go through some of the, again, some fundamental concepts which involve the idea of how an operating system starts working, the booting process, and then we'll move on to discussion about the different utilities, like the system programs, the different interfaces, and how system calls work. So that will be covered in the second half. So let's begin the first lecture, and this lecture will be about an overview of operating system. So let's begin by defining an operating system first of all. Then we'll look at the structure of a computer system to appreciate the role played by an OS in running a computer system. Okay, so we'll try to understand the role of an OS. Then that will motivate us towards the goal of an operating system. So what exactly is an OS used for? What is the role played by it? We'll talk about different tasks performed by an OS, and we'll see some examples of an operating system. Okay, so let me quickly go through the definition. So as you have been working with OS for quite some time, and we are used to this particular program, right? So the question that obviously comes up is, what is an operating system? Well, as you see below, we have shown, if you ask this question to different people, then you will get different kinds of answers, right? So either it would be like somebody would say, okay, it helps me to browse the internet. Some says to run my packages. Some say to develop programs. But whatever it is, the idea behind an operating system is finally to use the system in an efficient manner, right? So this is the basic motivation, that we would like to run the computer system in an efficient manner, and operating system is kind of, you can say, a middleware that utilizes the hardware and the software effectively so that the user can run the computer system in an efficient manner. Okay. So what exactly do we mean by efficient? So in order to appreciate that, okay, OS helps us to run a computer in an efficient manner, let us first try to understand what exactly the OS manages in a computer. So if you try to define a computer system, it is actually divided into two parts. One, the mechanical parts, or we call them the basic resources, the computing resources. So it's after all a machine, right? A computer is nothing but a machine that is instructed to do some tasks. And who instructs that? Well, it's the user. So when I say computer system, if I talk about the different components of a computer system, I can mention three different components of that. One is the hardware, the other is called software, and the third is the person who utilizes them, or we call them the user. So what is the hardware? The machine itself, the mechanical parts, which you utilize to solve your problem. So the idea is that the user has some problem to be solved. He also decides or designs the solution for that. And then he takes help of a machine. It provides the solution to this problem. So the solution to this problem is provided, and this machine runs based on the solution provided and gives you some result. and the user checks whether the result is according to his or her wish or the idea. And if it's perfect, then you say that, okay, my solution, the solution to this problem is validated, and I'm happy that I have obtained a solution to the problem. Now, because the user cannot run this solution in a limited time or it becomes very tedious, it takes help of the machine. So the machine itself is the computer. What does this machine consist of? Well, it consists of a lot of electrical and mechanical parts. Primary among them is something called CPU, which runs those instructions that you give. Then we have a storage element called memory, which holds these instructions. And these instructions or this data which is required by this computer is provided from an external world by some mechanism, by some devices. We call them input and output devices. So overall, this is the hardware that a computer is made up of. A computing unit, a storage location, and some devices that provide the data. So the role of the OS is to manage these devices. Okay, how does it manage? Well, this particular machine has to be instructed. We have already seen that in some of the other courses, that they have to be instructed. And when we say that it has to be instructed, there is some rule that must be followed. What is the rule? The rule is that this machine, which we call the computer, it meets these instructions or these instructions that we ask this particular computer to execute, has to be first put in this memory. So this storage location called memory will have these instructions one by one. Instruction number 1, 2, 3, 4 in this way. So these will be the instructions that are given or stored, and the CPU will be asked to get them one by one and fetch them and execute, and if required, write something. So we call this mechanism of executing things as a fetch execute cycle. Every processor will fetch instructions, execute, fetch, execute. This goes on until all instructions have been fetched and executed. This is the mechanism by which a computer operates. We call this a stored program model or von Neumann model. This is the ideal way of operating a computer. Write instructions, put it in the memory, instruct the computer to execute. How? Well, this computer or CPU also has some special storage locations called registers, and they are the ones that point to different locations in the memory. For example, this is a pointer called program count. This is how you do it. So this is the computing resource. So an OS is supposed to manage this computing resource. We'll talk about how. The second component that a computer is made up of or is required to be designed for computer usage is the program. We've already seen that. What is a program? Well, it's nothing but a set of instructions. And a collection of program is a software. So you may have one program, you have multiple programs, you group them for a particular purpose, and that's what you call a software. For example, you want to use, you want to write something, and you want to put as an input some text, you want to store that. We call it the word processor. It's a software, and this word processor consists of a lot of programs. A program that allows users to write, a program that checks the spelling, the grammar, etc., which a program to save the content. So all these are independent programs, and together they form a software called the word processor. We have a software that helps you to browse the internet, to get connected to some other computer, transfer files between them. That's called a web browser. That also is a collection of a lot of programs. And every program is a collection of a set of instructions. We have a program to store huge amount of data in an organized way. We call that as a database system. Well, so these are all programs, right? So we give them a special name, application programs, because they are meant to run or perform some task, some specific task. That is why we call them application program. We'll see some other kind of program as well, whose job is not to execute something, or not to run or do some task, but they help other programs to run tasks. They are called system programs. One of those is a compiler. We'll talk about that, and we'll also see some other system programs. So we classify these collection of programs again into two categories. One that is supposed to perform some tasks, writing some text, or storing some data, running a game. All these are application programs. And there are some collection of programs that help other programs to run. They're called system programs. You can put operating system into that class as well. But we'll for the time being keep operating system as a separate, because that's a very, very special program. Well, so the idea is that the OS is supposed to manage these two. It has to control and coordinate the use of this hardware among various users and applications. So that is the basic job of an OS. Why? It is because as long as you want to run one program on one computer, that is your hardware, that you have one CPU, one memory, quite a few IOs, and you just want to run one program, you are happy with that. That is how things used to be earlier in the late 50s or 60s when the computer was developed. You were just happy with running one program. One program, one hardware, one CPU, one memory. There's no issue. That's absolutely fine. And we call that a bare machine model. This is how things were working. But later on, people thought that this is not the right way, because you lose the performance of the system. You want many programs to be run. That is the utility. Okay. And as we saw, that softwares are collection of programs. You want all of these programs to run together. You cannot be happy with running just one program. Now the question that came up is, if you want to run many programs, multi-program environment, then obviously there will be a lot of challenges. What are the challenges that are going to come? We'll talk about that just. So in order to address those challenges, there is a special kind of a program that is designed that overcomes these challenges and helps the users and applications to run efficiently. Even if there are many applications, if there are many users, and there is only limited hardware, remember that you cannot apply the bare machine model individually for all applications. It's not feasible. You cannot have a dedicated CPU for only one program. So if you want to run 5 programs, you should have 5 CPUs. Or 100 programs, you will have 100 CPUs. Is that possible? It's absolutely infeasible. Why? Because hardware is costly. You have to find out a suitable way of sharing these. So the computing resources that we find, the moment you want many applications and many users to use them, they have to be shared. There is no way. So the idea is, how can you manage this sharing? How will this happen? How will you coordinate? That is the role of an operating system, to control and coordinate the hardware, or I should say the computing resource, because it involves all the, not only computing, but the storage resources as well. It's also involved, coordination of memory. Okay, this is the main goal of an operating system, to coordinate and control the hardware. We'll divide this into 3 different goals. Okay, so before I go into the goals of an operating system, I would like to first address the challenges. Which challenges are we talking about? The challenges while running multiple apps. So you want to run multiple applications on the same hardware. Okay, we already have seen that, but it's just a recap, quick recap. What are the challenges? The first challenge that you will find is, we just saw that while writing programs or working with programs, it's not always computing. You also involve, certain programs also involve access of IO, right? If you look at the structure of computer, or so in apart from CPU and memory, you also have some IO devices, and these IO devices are the ones that provide the data. If you are running only one single program, then to access the IO, you need some additional code, and that will be part of the program. So if you are supposed to write or execute a particular program P, and this program is supposed to execute some IO access, if it requires some IO access, this IO access in turn is another set of program. Let's call it Q. So you see, to write or to execute this entire program P, it also involves understanding of the details of this IO. Okay, so the details of the hardware should be known to the user. This is the first problem. Why do you think it's a problem? Because there are a number of IOs, there are different types. Some is, say, a keyboard, a mouse, scanners, whatever. So you see, there are different categories of input-output devices. So if I'm an user, if I have to write a code, do I need to know the details of every device? It's very, very tedious. And why should I do that? So the details of hardware should be known to the user. That's the first problem. It's not about multiple apps. It's about, even if you are running a single application, even then, that application, if it has to access an IO, you have to know the details of the IO. That's a very tedious job. Can there be a better solution than that? I don't want to know the details of that. Can somebody else do it for me? That's exactly what we'll see an OS does. The second problem is that every application, it uses the same code, right? Because here you see, if the IO access, if you are working with IO access, IO device 1, if problem P, a program P requires this IO access 1, it will be requiring Q. Suppose there is another program called R that also was expected to have the access of IO1. So that means this is again utilizing Q. And now think this particular memory has both P and Q, both P and R. So that means including the code for Q. So this program P will also have the code for Q. Program R will also have code for Q. So every app will be using the same code. Why? Why do you need to, duplicate things? Because after all, you are wasting space. Can there be a better solution than that? We'll come to it. So this is the second challenge. If every application will be using the same IO and access of that IO is the same code, why are you duplicating that? What is the need for it? Why can't you use only one single piece of the code and let all of them share the same piece? That is the question that should be asked. The third challenge that happens is, how do you manage these resources? How do you manage the resources among multiple apps? Okay, because the problem is that you have only one CPU, you have one memory, and you have a lot of candidates. Many programs want to run. How do you do that? Okay. Okay, so there's a question which says, why do we need to know the details of the hardware to be accessed? Well, it's very simple. If you are writing the piece of code for access of hardware, this hardware, this IO, okay, is a device which is having its own characteristic. Some devices are, they provide data in the form of characters. Some provide data in the form of blocks. So every input output device that you connect to your system has in own way of working, right? So this is a problem. So what we usually do is the IO device that you are accessing, every IO device has a controller associated with that. The controller is, you can say, an interface. It's a chip that understands the language of the physical device, and this side, it understands the language of the CPU, the processor. So if a CPU has to access this device, say a keyboard or a mouse or a scanner, whatever it is, or a printer, the CPU first has to instruct that device by programming the controller. Okay, so every device has a controller. The controller has to be programmed, only then the device can be accessed. And controlling the program or programming the controller is in itself a set of instructions, special set of instructions. And every input device will have its own controller and automatically will have its own set of instructions for programming the controller. So if you are a user and you want to access, let's say, n devices, that means your program should have the programming code of all those n devices. That makes things bulkier, tedious. Okay, so this is the problem that we usually face. The details, the programming details, how do you program the controller? The user itself has to know. That's the problem if you don't have someone else to help you. Okay, the third problem is you have to manage the resources among multiple apps. Who will get a chance to execute on the CPU if there are many candidates? Somebody should decide. And fourth is one application may disturb the other. So we have one app may encroach in the space of the other. This is again a problem, right? What will happen? One will disturb the other. Some fault in one of the program will eventually cause a disruption in the other program. You don't want to do that. This is the problem that we would like to solve. So these are basically the four challenges that we have. The details are to be known by the user. Every app uses the same code, which is a redundant thing to do. Because the resources are shared, there must be some management technique. And the third and the fourth is when one program is running, you don't want to disturb the other program. If there is some fault in a particular program, it should remain within that particular space of the program. It should not spill over to another program. That's what it is. So these are the four challenges that we have. And this is what is handled by an operating system, right? So the goal of the operating system is to overcome these four challenges and help the user to run programs. So what it does, the three goals of an operating system, which tries to address those challenges, can be written as number one, abstraction. Number two, virtualization. And number three, isolation. So these are the three goals of an operating system: abstraction, virtualization, isolation. The first two challenges, where we found that the user has to know the details of the hardware and every app has to use the same code, that's handled by the concept of abstraction. The management of different resources among different competing apps is handled by the concept of virtualization. And protecting one application from the other is done through isolation. Now let's one by one go into the details of each one of them. So as you see, can you please, there's a question coming up. Can you please speak out? What do you mean?
हेलो सर।
क्या?
सर ये समझ में नहीं आ रहा कि अगर जैसा कि हमने ऑपरेटिंग सिस्टम में कुछ भी है तो हमने प्रोग्राम लिखा, तो उस प्रोग्राम से मतलब वो हार्डवेयर को कैसे पता चलेगा कि हमें यही करना है, मतलब प्रोग्राम से?
You want the hardware to be, you want the access of hardware.
यस सर, मतलब ये हमने लिखा कि इन दोनों नंबर को ऐड कर दो, ठीक है, तो वो प्रोग्राम को देख के वो हार्डवेयर को कैसे पता चलेगा कि मुझे ये दोनों को ऐड करना है?
No, it's you who has to told. There is a set of, see, say for example, as you put that I have to add two numbers, right? Now the hardware is nothing but a machine. It does not have its own intelligence. You have to do that. That's what we were talking about, that you have something called a CPU. The addition of two numbers, you have to write a solution for that. You have to design a solution for that. Okay. So suppose your task is add two numbers. You have to design a solution for this, and you have to design the solution, write it in the language that is understood by the computer, put it in the memory, and instruct the CPU to execute them one by one. Right? Please try to understand, computer is no magic. It does not work in its own way. What you make the computer use is, you have a solution in mind. This is how I want to solve that. You write the solution, but you have to test whether the solution is correct. The problem with this testing is that how many such tests will you perform? Number one. Number two is, if you go on testing for a certain number of input values, it's doable by a human. But beyond that, it's impossible. So to ask a machine to do it for you, that is why you require the computer. You use the computer to validate your solutions. You write the program, you write the solution, you give the solution to the computer, to the machine, and ask the machine to run the solution in a very fast way, which the machine can do on a certain test inputs, and you check whether it is giving you correct values for those test inputs. If it is giving you correct values for almost all the test inputs, you are convinced that it is correct. Okay. I think you are taking a course called Theory of Computation, where you are told how to test whether there exists a solution for a problem. Please try to understand, machine is it's a computation model with a certain limitations. There are only certain classes of problem which you can solve using a computer. Right? A computer is just our machine which is utilized to solve or validate whether our solution is correct. It is not a magic. Okay. I'm talking about procedural based. Okay. We deviated a bit from. Fine. So this is the goal of an operating system: an abstraction, virtualization, and isolation. Okay. Providing or hiding the details of a hardware from an application is what you call abstraction. What do you mean by that? We mean it's something like this. This is the hardware, and this is the application, right? Now, an application, when it requires an hardware, I just give you an example. Suppose you have written a C code, right? And you have a code where you have used some command called printf. Your idea of using this printf is to print the characters on an output terminal. It's on an output screen. So this line is nothing but an access of a hardware, which is an access of an output device, right? So as we just mentioned, the challenge was that all details about access of the hardware should be known. But do you ever care about it? No, you simply use this function and you are done. So who takes care of all this? Well, this printf is a call or a request to a special software called operating system that sits in between, right? So whenever an application requests for an access of a hardware, it is actually a request to the operating system. And the operating system, in turn, forwards this or goes and accesses the hardware, the IO, gets the result and passes it on back to the application. This is how things happen. So application puts it to the OS accesses the hardware and puts it back to the application. So you see, the application doesn't need to know the details of the hardware. It doesn't need to know details. The OS is taking care of everything. We'll see how OS takes care of that in more details later on. For the time being, let's try to understand. The OS takes care of all these details and just passes on the information back to the application. Okay. Now what and how does this happen, by the way? So the application, it puts a request to the OS in the form of something called a system call. We will talk about system call in the next half of this lecture.
Excuse me,
So
sir.
yes.
Sir, so we only communicate with the input, communicate through the input-output devices. Operating system will do all the coordination which is inside. Is it like that, sir?
Yes, it is.
Okay, sir.
Because the application, or you can say user, whatever you call them, is not supposed to access the hardware. There are two utilities of using this principle. One, the application you see doesn't need to know the details of this hardware. Do you know? All it just needs is, how will I inform the OS what hardware to access? How will I inform the OS what hardware to access? That is what the app should know. Rest, everything is hidden. So the system call, you can say, is some kind of an API, or we call it application program interface. Let me give you an example. When you are turning on the switch of your fan, okay, you don't need to know how the electricity is passing, how the motor is going, nothing. You simply go and turn on the switch, and you know that if I turn on the switch, the fan will move. If I turn off the switch, the fan will turn off. That's all. So as a user, I don't need to know how the fan is going to move. How is it going to, how the motor will rotate, how will I get it, how the electricity will pass. I just go and turn on the switch and that's it. So the switch in this case is the interface. That is how I am interacting with the fan. And I need to know the different, how to use the interface. If I turn on the switch, if I take it up, it's an off position. If I take it down, it's an on position. So I need to know the contents of the interface and how will I be using the interface. I don't need to know the details of the one that is controlled through this interface. So operating system gives me this kind of an interface to access the hardware, and it takes care of the details. So the interface that this gives me is these system calls. So these system calls are the interface through which I interact with the OS. And OS gives me a list of all those system calls for different purposes. You want to access an output device? Well, this is the system call you should have. You want to interact with, you want to read something from the input device? Well, this is the interface, this is the system call that you should have. So it gives me a list of all the system calls, and I choose the one that I should have, pass it on, and that's the request to the OS. The OS interprets that. Oh, it has asked me to execute this system call. This means he asked me to write something. This is a system call called open. It wants me to open a file. So in this way, it understands. Clear? This is basically the idea of abstraction, hiding the details. That's the first utility. Second utility of having this abstraction, I mean, you don't need to have in addition to the details being hidden. The second challenge that we had, reusing the code, that is also done. How? Well, that's very easy. If one particular program is going to execute some IO, right? If suppose, let's take an example. If this particular program is going to have an IO access, this program is also going to have an IO access, and all of them are going to access the same IO, right? Same IO means they both will be using the same interface and everything will be hidden by what? The OS. So OS is also a special program, and which contains all these details of every hardware, right? So the details of every hardware are present in the OS. And interestingly, all programs that would like to access a certain hardware has to follow the same rule. What is the rule? Rule is everyone will put a request by using a syscall, and the OS will grant that. You want P1 will be requesting, fine. P2 needs to, P2 has to put a request for the system call. Okay, so P2 will also be granted. So there you see the particular piece of the IO access mechanism is handled by the OS and is not part of the process. It's not part of the program. It is bundled in the form of utilities, right? It's bundled in the form of utilities, and just every program that wants them has to put a request by looking up to the corresponding system call. That's it. So it doesn't have to keep it within its own space. This is the space allocated to P1 in the memory. No need to keep that access P2. No need to keep that particular code. Everything is in the OS. You put a request, the OS will provide you. That's the utility. See? So you don't have to, every app, because it is using the same code, doesn't have to include that piece of code. It will be bundled as a separate piece of software or a portion of the special program, right? That's how it works. This is basically the concept of abstraction. Okay, so we have to know the corresponding system calls. That is exactly what will be treated or shown to you in the lab. Okay, the next challenge, managing the resource. And this is handled through the concept of virtualization. Let me quickly talk about that, and then we'll move forward. So what is this virtualization concept? As we have already seen, okay, let me move ahead. I've already discussed about this, the hardware abstraction. How does the abstraction happen? No more details required by the programmer. Application can reuse the OS functionality. That is what I mean by all applications can make use of the utilities bundled in the form of OS. The OS provides some interfaces and which are consistent. That means these interfaces do not change with application. Interfaces are constant. Every application that wants to access a particular hardware has to know that interface, and it will be using the same interface. If it is an interface called write, this function is common for all applications that will be requiring to write. They will be common to all of them. There is it's not that one application will have one name, the other application will have another name. No. Every application that wants a particular system call will have the same. So the interface is consistent. This is the beauty of abstraction. No details required. Reuse OS functionality. OS interfaces are consistent. You just have to know the name. That's it.
हेलो सर, मतलब
Yes.
सर आप बोलना चाहते हैं कि ऑपरेटिंग सिस्टम में हर एक हार्डवेयर का यूज करने का प्रोग्राम सेट किया रहता है कि मतलब
जी,
कीबोर्ड को
yes.
कैसे यूज करते हैं, माउस को कैसे यूज करते हैं.
Correct. Yes, that's there. And we call them special programs called drivers. I'll talk about that.
हाँ, यस सर, जो हम लोग पहले डालते हैं.
Yes, they are called drivers. We'll see. Is the concept clear?
Sir, I had a question.
Yes, please go ahead.
Sir, why is this abstraction like why like by abstraction we can the user cannot access that code, right? So like why is it hidden is what I'm.
Yeah, it is hidden. First of all, do you need to know the details? Why do you need to know the details? It is creating complexity for you, number one. Number two is, if by chance your application is using some hardware and somebody else is also using the hardware, and you have messed up your application, which means that particular hardware is not accessible to you but due to your fault, somebody else is also having a problem. Is that a correct way to do things? No. I'll show you a code where you will see the difference. So why should you create trouble for others? Why can't that be managed by someone else? If I ask you to teach something, and if somebody else has also asked, does the same, you both will mix up things. Rather, why can't I take up as a teacher, and we'll both will be I will be instructing the same thing to both of you. You have a problem, okay, I'll deal with that in a separate way than the problem of the other student. That's it. Is that okay?
Yes, sir.
So it not only hides the details, reduces complexity of the user, it also ensures that one program does not hamper the other one. Okay, because hardwares are very, very costly and they are shared. Remember, you cannot have somebody using the same resource and creating trouble for others. No, that's not allowed. Okay, so this is abstraction. Okay, I've already discussed about that. Just to detail out.
Sir, what is the
Yes.
meaning of application remains the same when hardware changes?
Yeah,
Sir.
it means that the system calls that we use, the process of requesting the access of hardware remains the same for every application. If I am using a browser and I want to write something, the request that I put to an OS, and if I'm using a text editor and I want to write something, and the request that I put to the OS, both will be using the same system call. They will not change. Okay, that's what I mean by consistent. The interface is nothing but the list of functions called system calls. They remain the same. There's a list and every application using the same list. You don't change it from application to application. Clear?
But sir, if we change from a monitor to printer, then the program would change.
No, that's okay. But I'm talking about across applications. If two applications are going to use the same hardware, that is the same IO, the mechanism to ask to the OS will remain the same for both. That will not change. The interface. Interface means the process of reading something, the process of writing something. Those functions, they are remaining the same. They do not change from application to application. If I want to write something or tell something by use of some function called write, this is the same function I will be using in all applications which will be requiring the write operation. I will not change it to some different other function. That's what I mean. It's consistent. So that's a standard thing, no? That's the beauty of that. So I don't have to remember all different kinds of functions. I know only a certain class because that's what OS has given me. You want to write something? Well, use a write function. If you are in application 1, that will also use a write function. If you are in application 2, that will also use a write function. System calls are, okay, so here you go. The common utilities to access hardware, have a look at this, are provided as services. I told you, it's like you go to a bank, right? Bank provides you different services, drawing of money, deposit of money, transfer of money. These are all services. The mechanism of each one of them have been identified. That is a separate form that you need to fill up for every transaction. You want to deposit money, there's a form. You want to withdraw money, there's a form. You want to transfer money, there's a form. And everybody who's going to do has to follow the same form. It's not, individualistic. That's what it means. It's called a services. You request for a service, you get the service. And the user programs request the OS for the services through interfaces. These interfaces are called system calls. The OS is divided into two. The OS comprises of two portions. One portion is which actually provides the utilities or the services. It is called the kernel. So if you look at the OS, here is the hardware. Surrounding that is the OS. The OS has two parts. The first part, that is actually touching the hardware or accessing the hardware and getting requests from the application, is called kernel. That's the bundle of utility we're talking about. That contains all the different IO access ports. Surrounding that, is another piece of software which is called the system programs. These system programs are utilities that help the applications to put a request to the kernel. We saw that application will need to request to the kernel. But even that is a very tedious job because you have to remember all the system calls, isn't it? We just saw that the way to request a kernel is, see, look at this diagram below. The program puts a request to the kernel through a system call. So that's also a very tedious job because the program has to know all the system calls, the details about the system call, how they work. I don't want to go into that complexity as well. So OS helps you by that as well. OS gives you another layer, which is called system programs. You make use of the system programs and you are done. What are these system programs? Let me give an example. There is a system program in Linux which is called the shell. Okay, it is called the shell. Shell is a special kind of a program. What is it used for? Well, as the name implies, it's a system program. So it is used to run the system code. What code? Every command that you give, say for example, in Linux, the moment you open up an application called terminal, right? Let me show you this. The moment I open up a terminal and I type in this, say I have, so this is, can you see this? This is the terminal, right? So I'm using the Macintosh operating system and this is the terminal that I have. So if I simply type in a command called, let's say ls, it displays all the contents of folders and subfolders. So what is this? This is a program that is running called shell. Okay, so I have a system program called shell that is running, and I have typed in a command called ls. Ls means list out the directories and subdirectories and files in the current working directory. Well, so that's what you get with that. So what happens is, let me come back. Yeah. So what happens is this shell command that you have, and when I typed in this ls, now this is a command that I typed in and I used it in this particular program. Now this ls was actually combination of a number of system calls. There was a number of syscalls which were there. What was it? Request to the operating system to display some content of the present working directory, name of the files and folders. See, you are actually asking an output device to be used, which is the monitor, where you will be listing out. And not only that, you are also asking the hard disk to be accessed, which is again an IO. So there are a lot of IO accesses that you are asking. So that means there's a lot of system calls involved in that. These are all requests. Say, for example, there's a call called write, which is a request to the OS to print something. There's a call called open to open a particular file. These kind of calls are here. But if you had to write this program, you had to know the details. Which are the system calls I should use? How will they be organized? How will they be ordered? Again, a confusion. So OS helps you in this as well. It gives you one again layer of abstraction where you simply write a program, a command, and that gets translated into a number of system calls. And that system calls are executed by the kernel and you get the result. Look how beautifully things work. That is how system calls are executed. They are not directly executed by the application. The application in turn uses some system programs. The system programs execute those system calls or list out the system calls and sends it to the OS. The OS in turn executes them. What are the system programs? Well, I've already told you that shell is one of them. You have compilers, you have debuggers. All these are different programs that help other programs to run. Which programs? The applications, obviously, that sit above them. What
Hello,
application
sir.
do they have? Yes.
Sir, I had a doubt. Sir, like when I'm simply clicking on a folder to open it, so that's also kind of a system call, like I'm asking the
Yes.
kernel to
Yes.
open.
You
So,
are.
so
Just that you are making use of a graphical user interface.
okay.
So there
So,
are
sir,
two
the
situations.
system program will be graphical user interface.
Yes, it's the desktop manager that you are working with. So there
Okay, sir.
is something called a desktop manager. You are sending out commands to the desktop manager. All your mouse clicks that you are doing is nothing but an equivalent of writing commands on the terminal. I am writing the commands. It's called command line interface, and you are clicking it by clicking on a particular area of the screen. Both are the same. You are actually invoking a system program, a desktop manager, and I'm invoking a terminal or a shell. And we are
Yes.
passing out a command. The command gets translated into a number of system calls. The system calls are passed on to the OS. The OS executes them, and you see the result. Okay. So
Yes, sir.
user programs, they request the kernel services through interfaces called system calls. Please get this thing very, very clear. That is the reason why I'm spending so much of time. This is the concept that I want all of you to understand. So user programs do not have the facility or privilege to access hardware. They can only request. The request is done through interfaces called system calls. System calls are nothing but function calls executed by the kernel. What are system calls? They're nothing but some functions. That's all. Special functions for different purposes. Not executed by the user program, executed by the kernel. That is why they are special. Do applications directly require execute system calls? Well, in some cases they may, in some cases they may not. In some cases they may use some other programs, such as system programs, which in turn will convert them into the list and provide it to the OS. Okay, next comes the concept of virtualization, which is the resource management. So resource management is done through virtualization. What is this? As you can see here, hardware is very, very costly. You have to share them. There is no way. You can at most have certain number of CPUs and you have to efficiently distribute that among the applications. Concurrent execution will require some trick to be played. We'll talk about that. So what is the role of the OS? OS is basically a resource allocator. It allocates the resources. To whom? Obviously to the applications. It decides which application should run when. How? Let's talk about that. Running a single program is not an efficient way to utilize a computer. You cannot. So what you should do is, you should go for multi-programming. Allow multiple programs to run. As you can see here, we want two programs, the GCC compiler and the Emacs text editor, to run on the same hardware. That means the CPU, memory. But how will that happen? How will I decide who will get a chance? So the idea behind this is that you want to run more than one process at once. You want to run more than one process. Okay. How? Now, the very nature of an application gives you this facility to run more than one process. What do you mean by that? Well, if you look at the program execution pattern, so if you look at what happens when a program executes on a CPU, okay, you will find that it consists of two cycles. It consists of an alternate CPU and IO cycles. That's what happens. What do you mean by that? We mean if you look at a program, there are certain instructions, let's say I1 to let's say IK, certain instructions will be running on the CPU. Okay. And there are certain instructions, let's say I5, this is an IO access. Some instructions of a program will be instructions to the CPU, some instructions will be instructions for access of an IO, like file handling, getting some value from the keyboard, printing something to the monitor. All these are IO access commands. So some commands will be CPU, some instructions or commands will be for IO. If I look at the pattern, I find that if this is how I represent the working of the program, I find that for some portion of the time, my program T runs on the CPU. I'm writing that as a shaded figure, and then it gets stopped. Stop means the CPU does not execute. Why? Because now some IO access is executed. It will remain this idle for some amount of time. Then again, CPU will resume because there are again some instructions which are CPU instructions. And in this way, things will happen. This is the pattern of execution of a program. That is why it says. Now this, if you are intelligent enough, you can very easily make use of these idle cycles. So these idle cycles are CPU idle cycles and they are not wasted, but you can make use of them. How? By allowing a second program to execute in between. When the CPU was free, because it is not running any program, because it is not running P1, don't keep it free. You allow second program to run in that, P2, because P1 is busy handling the IO. That is the advantage here. That is what we mean by you can run more than one process at once. That means it says when one process blocks, that is, it is waiting for a disk or a network or a user input, waiting for something to get from the keyboard, waiting for a file to be read. It's an IO access. This program gets blocked. We say that it goes into a blocked state. Start running a different process on this or a program. This is the utility of multi-program. So what is the thing that you are doing? You are actually tricking the process or the program to believe that as if both the program is running and the entire CPU is allocated to the same program. Okay, its entire CPU is allocated to the same program. So this is a virtualization technique where you believe that the two programs are having an individual CPU. However, not. You are actually sharing the CPU among the two programs, but both programs are believing that they are sharing the CPU. This is called virtualization. Single CPU or single user, it cannot keep the CPU busy. Why? Because IO devices will be accessed, so you cannot keep them busy. The goal of any program would be to make the CPU busy as much as possible. You don't want the CPU to remain idle. Multi-programming is the one that handles this. It organizes the job. So the CPU has to execute. How? You have a subset of total jobs, which is kept in the memory. Let's say job 1, job 2, job 3, job 4, and you switch between them. Sometimes job 1 will be executed. The moment it gets blocked, take it out of the CPU. CPU will not execute. Give a chance to job 2. Job 2 will execute. Job 2 during execution may get stalled because it is also goes into an IO access. Take it out. Give chance to job 3. Go on doing this cycle. Okay. Who does that? Well, this is called job scheduling. This mechanism of moving one job from the CPU, taking it out, putting another job schedule. Job means programs, right? This is the job of the OS, the scheduling, primary job of the OS. Okay, got it? The idea of virtualization. What are we virtualizing here? Well, we are virtualizing the CPU. We are virtualizing the CPU in this case. Okay. Okay. Now we will go to the next. I'll just give you a brief idea, and then we will take up virtualization of memory. Okay. The next virtualization. The second virtualization that the OS does is virtualization of memory. What is that? Well, when you are running more than one program, you're keeping more than one program in the memory. Okay. For here, let's say P1, P2, P3, P4, and you are scheduling them. That is, sometimes you are taking P1, sometimes you are taking P2, sometimes P3, P4. We just saw CPU scheduling. Now, suppose P1 was taken out. Let's understand the situation. Suppose P1 was executing currently. It hit upon some, or maybe say P1 was executing and P1 finished. P1 finished. You got a chance to put P2. Okay. Now, after some time, P1, which was residing in the external drive, again wants to come and sit here. Again wants to come and sit here. But the problem is, now the space which was previously occupied by P1 has been given to some other process, let's say P5. And P4 is now over, so that if P1 wants it, P1 can come and sit here. You get the idea? Initially, P1 was in some place of the memory. It executed, was over. Suppose you opened a text editor. P1 was, let's call that program P1, text editor. You worked with the text editor. At that time, a browser was there, a multimedia player was there. And then the text editor job was there, you closed it. After some time, the memory, portion of the memory where the text editor was put, the text editor program was put, now has been given to some other process called P5. Process program, whatever you call it, P5. Let's say browser program. Now again, you click the text editor. Now the problem is, the text editor is no guarantee that will go and sit in the same place which it was sitting previously. Why? Because now it is taken up by some other program. So what to do? You find out some other place and put. Now look at the problem. The problem is the CPU, if you fix up the address of the P1, when you remember when we were writing programs in assembly, we used to write, okay, jump to a particular location called, let's say 2050 hex. This is how I write a program. 2050 hex is some program, some line here. This is how your programs are. There is a mention of addresses in your program. It's always there. Now think about the problem. Suppose when P1 was sitting in this portion initially, then your program had mentioned 2050, and 2050 was an actual location in the memory, which is like this one, 2050, and it was working perfect, right? Now think about the new situation. When P1 now comes and has to sit here, but you have not modified the program, your jump address is still 2050. But 2050, if you ask to jump, is actually this location, right? But P1 is not in this portion. So how can you ask it to jump to this particular address? You should have told it 4050, maybe let's say 6050, which is this time the actual location of the statement or the line where you should jump. I repeat, there was a program called P1, which had an instruction called jump to a particular location, 2050. And the 2050 was okay because when initially P1 was sitting in this portion of the memory, 2050 is actually this location. So it was fine. Whatever you wanted to jump to, it jumped to the correct location. But now it was taken out. It finished and reloaded. But when it got reloaded, it came and sit in a different location in the memory. And now you cannot write 2050. It's wrong because it is now, it should jump to a location 6050, but you have not modified the program, right? You have not modified. See, so what to do? Is the problem clear to everyone? The reference to a particular address, the reference to a particular address in the program has not been changed, but its actual location where it should sit has changed. This will result in a problem, right? You got it, the idea?
Yes, sir, I got the idea. But sir, like, is this somewhat like a stack? Like, which program will be executed first here? P1.
That's what I'm saying. That these addresses that you are referring to, it cannot be a fixed mention. They must be relative. You cannot fix it. They have to be relative, right? They have to
Sir,
be
so the address will
decided.
keep changing.
Yes, and they cannot be absolute. They cannot be an absolute addressing. It has to be relative addressing, right? It has to be relative addressing. You cannot have an absolute addressing because now it is sitting in 2050. Tomorrow, the next time it may be 6050. So it has to be relative. Relative with respect to what? Relative with respect to the range which has been allocated to you now. With respect to that, you should decide. How will this happen? How will this happen? For that comes the concept of something called virtual memory, right? So we introduce the concept of virtual memory. What is this virtual memory? I'll just give you a very, very brief idea because we actually devote a complete lecture on, or in fact, a topic on this particular concept. So what is virtual memory? It's a conceptual memory, right? It's a conceptual memory. The memory as seen by the CPU. It's called virtual memory or logical memory. What is that? Let me give you a very brief idea. Suppose you have a program P1, and the program P1, when the user has written, it means there's a list of instructions. This list of instructions that you have written, as just the example that I gave you, may have some addresses mentioned in that, which will be relative addresses. Relative addresses, like I will not give fixed address to that. Rather, I will give any name. Let's say I give a name A plus 1, A plus 2, A plus 3, A plus 4. And if I have an instruction called jump and I want to jump to this particular location, I will say jump A plus 1. I will not give the exact value. Why? Because sometimes maybe A will be mapped to a location 1000. Next time when this same program will be put in the memory, it may be mapped to 5000. And accordingly, these values will change. So I don't have any problem. Instead of fixing up the absolute addresses, I will be fixing up logical values for that. So my program will be having this kind of view that all my instructions, as if they start from location number 0 onwards. The question is, how big a program can you create? Well, as many possible addresses you can generate. If suppose I have, my processor says that I have an address bus of size 32-bit, 2 to the power 32 addresses you can generate. So my programs can start from 0 up to 2 to the power 32 minus 1, these many addresses. So your program can be as big. What are you doing? You are actually removing the restriction of an actual location associated with the program. You are generating the program believing that as if the entire memory will be allocated only for this program. I repeat, you are writing a program and you are allocating addresses to each instruction of the program, believing that all addresses of the program are only for this particular, all addresses of the memory are only for this particular program, as if only this program will be residing in the memory. You're doing it in this way. Fine. So you are writing it in this. So this address range that you create of this program is called its logical address. It's called its logical address. It's the address associated with a program after you compile that. Please understand, and I'm spending so much of time in making you understand. If you have any doubt anywhere, feel free to ask me. This is one of the most important concepts in OS, the concept of virtual memory. A lot of things rely on that. Please understand this.
So, basically, we are allotting a range instead of allotting a particular value in the memory.
Absolutely. Instead of actually allocating the actual address in the memory. Now, these instructions will actually reside in the memory. But instead of allocating them or fixing them to a particular specific address in the memory, they may sit anywhere. I don't care. But I am not interested in that. I will give a range of address. I call them as logical address.
And
so here is a program.
It can depend on any other program also.
I'll come to that. Let's take up, let's say process P1, program P1. Program P1 has a range of addresses given to that. When does this happen? This happens right after compilation. So the addresses associated with the compilation output is a logical address. Let's say some 0 to some max -1. This is what happens. This is for P1. Similarly, there's a program called P2 that also has been compiled. And that can also be given from 0 to max -1. They are independent when logically considered. This is the logical address range. This is not actually the addresses allocated to the particular program. No, they are the ones which is logically given just immediately after compilation. Now what happens? But the problem is they will physically reside in the memory, right? P1 may be here, P2 may be here, P3 may be here, anywhere. They can sit anywhere. So what I need to do is, when a CPU will be generating an address, right? Suppose it wants to generate or it wants to access some instructions of P1. Understand this. When CPU will be generating some address for P1, suppose this particular address, CPU doesn't need to know where is P1 actually sitting in the memory. It doesn't need to know. It just generates an address, and the address is the logical address that it generates. So the address that it generates is actually this address, not this address, not this one. This is the actual location, but it generates addresses here, this one. But this is not the place where this particular instruction is residing. It is residing here. So who will give the CPU this particular instruction? So here is a thing called OS. So the address that is generated considering the logical address of the process P1 is taken by the OS and converted into the actual physical address of the process. So the logical address gets converted into the physical address of the particular program. The memory location of that is accessed, and once the instruction is obtained, it is sent to the CPU. What is the advantage of having that? The advantage is no problem. The logical address will always remain same, because the logical memory means the address range allocated to that particular program. That is always contiguous. That is one after the other. This instruction will have the same logical address throughout. It will not change. This particular instruction will have a fixed logical address for this program. Its physical addresses may change. Why? Because now P1 is here. Maybe next time P1 will be sitting here. So the logical address, the physical address of this instruction may be next time here. No problem. It's the job of the OS to handle that. So CPU will be generating the same address because it is looking at only the logical address and generating. It is not looking at the actual physical address. So there is no problem.
Excuse me, sir.
Yes.
Yeah. Sir, So the logical address will be one fixed thing, and the other one will be a range. Is it like that, sir?
Logical address is a range that is fixed.
Logical address is a range, and
Yes,
virtual address
that's
is fixed.
No, that's logical itself is virtual. Logical and virtual are the
Logical is
same thing.
virtual, and
And
sir, if it is a
physical,
range, then okay, physical is a range, or logical is also a range.
whenever a particular program is compiled, a list of instructions is created. Correct? Suppose you think it in this way: a program has been created, and there are some set of instructions which are created, and every instruction is given a particular address: a plus 1, a plus 2, a plus 3, a plus 4. You call it 0, 1, 2, 3 in this way. This addresses that you have allocated is the logical address or virtual address, whatever you call it. The CPU will be looking at or will be seeing these addresses. Now, sometime this 0 will actually mean, see, this program has to finally reside in the physical address, isn't it? Sorry, in the physical memory. I will mention it this.
Yes, sir.
So a program has been generated, a list of instructions has been created. Every instruction is getting an address. Let's call it 0 to say, let's say there is a list. Let's consider 5. 0, 1, 2, 3, 4. This is program number P1. This is the logical addresses I have generated. Just after compilation, I've given an address for instruction 1, which is 0, for 2, 1, for 3, 2. In this way, I've given an address number to each one of the instructions. This is what the CPU will be looking at. CPU will see this. Okay. Now, this program P1 will finally reside in a memory. This is the concept. This will finally be residing in the physical memory, in the RAM. And P1 will take 5 locations in the memory. 1, 2, 3, 4, 5. Let's say this is where P1 is sitting. This is actual locations of the memory. It is like 0, 1, 2, 3, 4. Now you see, logical address 0 is mapped to physical address 0. Logical address 1 mapped to physical address 1. Logical address 2 mapped to physical address 2. This can be one possibility. What can be other possibility? Other possibility is, no, P1 is not sitting here. P1 is sitting here. Again, 5 locations. Let's say 8, 9, 10, 11. So in this case, if this is where P1 sits, logical address 0 mapped to physical address 8. Logical address 1 mapped to physical address 9. Got it? This can be another possibility. So physically, P1 can sit anywhere. So wherever P1 sits, the corresponding physical address is allocated to that. And you have to map a logical address corresponding to the physical address. If it sits here, it is 0 with 0, 1 with 1, 2 with 2. If it sits here, it is 0 with 8, 1 with 9. That's how it is. The advantage is that CPU will always generate the constant address, which is the logical address, because logical address is not changing. It's a concept. It's the range that you have created. Its mapping is what you have to keep track of. Sometimes P1 will sit here. Sometimes P1 will sit here. So if P1 sits here, its mapping will change. If P1 sits here, it will have a different mapping. So who will keep track of this mapping? Who will keep track of this mapping? This
Logical address.
This is the job of the OS. The OS keeps track of the mapping between logical address and physical address. Every program that gets generated, all instructions of that get a range of addresses. They are called logical or virtual addresses. Every virtual address has a corresponding physical address associated. I repeat, every logical address has a physical address associated with that, because the program is during that time sitting in the memory. So it is having an address. So every logical address will have a physical address. This mapping the logical address of a particular instruction corresponds to which physical address may change because they will be sitting in different portions. Okay. Yes. So somebody says, how does the OS know? That is what we are going to cover in the topic memory management. Don't worry. There are a number of techniques which you will learn. One of them is called paging. Second one is called segmentation. Third is called paging and segmentation. We'll talk about all that. Is the concept clear? So what is the virtualization here? Virtualization of the memory. It's like every process or every program feels that the entire memory belongs to it. No, it's shared. Maybe P1 is sitting here, P2 is sitting here. So it's like this. Similar to what P1 had a logical address, P2 also has a logical address. Okay. So this is mapped to the 0 of P2. This is mapped to 0 of this. Look. So logical addresses of P2 are mapped to the corresponding physical addresses of P2. Logical addresses of P1 are mapped to physical addresses of P1. So every program feels that the entire memory belongs to me. It's not. They're actually sharing the memory among other processes, but it feels that I am. And the good thing about that is the CPU, Manpreet, can you just spell your question?
Sir, what if the physical address अगर program का overlap हो जाए, sir? जैसे memory में दो program
we will come to that. We'll just come to that. That's the third goal. We will come to that. That's called isolation. That's the third goal. You have to ensure that. Okay.
Yes.
So the good thing about that is the CPU, because it does not see, the CPU sees the logical address of a program. Okay. Because the CPU does not know the actual location, it does not have to change. If tomorrow P2 shifts from here to here, no problem, because CPU is not generating address looking at the physical location of the P2. It is generating looking at the logical address. And logical addresses are the same. They are not changing. Okay, so what you are changing is the mapping of logical address to the new physical address. And that is taken care of by the OS. So because the logical address is not changing, CPU is not generating any other address. So that is the utility of having the OS taking care of the memory. Is this clear, everyone? The concept of virtual memory. So virtual memory is the range of addresses allocated to a particular program. Every program, and that is a continuous range of address. How big a range can you create? The number of addresses that you can generate out of CPU. Every program will have a logical address. CPU generates addresses keeping in mind the logical address of the program. Now, since programs actually have to reside in the physical memory, every program will have a physical address as well. The mapping between the logical address and the physical address is handled by the OS, so that multiple programs can reside in the memory. They can reside anywhere, even if they change their location in the physical memory. Even then, that's not a problem, because CPU does not have to change the address. It generates address according to the logical address. Even if the program changes its position in the physical memory, the logical address remains constant, and that new mapping has to be decided, which is taken care of by the OS. This is virtualization. Even if it is shifting the position, it's virtual. The memory is virtual because every program is getting a virtual range, which is seen by the CPU. Is the concept clear to everyone?
Sir, you mentioned that the memory allocation is continuous. So is the logical address allocation continuous or allocation in the physical memory?
Logical. Physical cannot be continuous. Physical cannot be continuous because, I mean, obviously the program, within the program, the range is obviously continuous, but a program can shuffle in the physical memory. I just give you an example. Initially, the text editor was, you had opened a text editor. It was sitting in some portion of the physical memory. You closed it and you reopened that. There is no guarantee that it will come and sit in the same portion of the physical memory. It may sit in some other portion of the physical memory. So the program, when it is sitting in the physical memory, can sit anywhere.
Yeah,
So
I
if
get
it can
that.
sit anywhere, how can the CPU keep on changing the addresses? So it has to apply a constant address. That is why the virtual memory has been created.
What I was asking was if there are, say, 10 instructions, a hypothetical
Yeah.
program which has 10 instructions. So those 10 instructions, can they be continuous in the
They are
physical memory?
They are continuous.
Okay.
They are continuous.
Yeah.
Even
and another question.
later on, I'll show you, even that can be possible. I can split it up into two halves, 5 and 5, and even those 5 can sit anywhere.
Okay.
That is also possible. That's what we are going to talk about in a concept called paging. Even I will split up those 10 instructions into two halves or maybe three halves. And the three halves again can sit anywhere in a distributed fashion. They not necessarily has to be contiguous. Even that can be handled. And that will be handled.
If contiguous memory is not necessarily required, that implies that dynamic memory allocation can also be handled by the OS.
Yes,
for any
yes.
program.
It will be. It will. I'll show you how. We will talk
Okay.
about that. Okay. Is the concept clear? Virtualization?
Yes, sir.
Yes, sir.
Should we take a break here maybe, and we'll come back with, or maybe this one small idea that I will first touch upon, and then we'll break and we'll start off with the next lecture. Is
Yes,
that
sir.
required, or should I continue with this?
You may continue.
Okay, I'll just take 5 minutes. We'll cover one small portion and we'll take a break for 5 minutes and I'll cover the rest. Okay. So we have discussed two goals of the operating system: abstraction, virtualization. There is one more which an OS should do, and it's called isolation. What is isolation? As the name implies, it should protect the programs from each other. It's important because if you don't do that, then it may very well happen that one may encroach into the other and will disturb. You don't want that to happen. So what is the way? How do you protect that? So for that, and most importantly, a program should not disturb the OS. Remember, when you are allowing programs to sit in the memory, you are also allowing the OS to be part of the memory. So OS is also a program that is also sitting in the same memory as other programs, P1, P2, P3, right? P4. So OS is also sitting in the memory. So suppose if you allow P1 to encroach into the portion of the memory allocated by OS, then you are inviting trouble. It can disturb. And OS is a special program. That is the one that is managing everything. So you don't want the OS to be corrupted, right? So the OS should be protected from the rest of the portion. That's the first idea. How we will protect one program from the other, I will come to that later. For the timing, let's talk about how the OS should be protected from the rest of the programs. So what we do is we categorize the memory into two portions. A portion that is occupied by the OS, it's called the kernel space. The range of addresses occupied by the kernel or the OS. And this memory I'm talking about is the physical memory, okay, the actual residing portion. So there's a range of addresses in the physical memory where the OS is actually residing. You allocate that, reserve that for OS. This is a special portion. No other program can run in that particular portion of the memory. It cannot read anything from there. It can read, but it cannot write anything to that. This is called kernel space. And this portion where other programs can write or can reside is called user space. So the first thing you do is you categorize the memory into two halves: kernel space, user space. When a program which is in the kernel space is running, you call that as a kernel mode. That is, CPU is running in the kernel mode. CPU is running in a kernel mode. It means that CPU is running a kernel program. Okay, it's running a kernel program. Running a kernel program means programs written within this range of the memory. Is that clear? If a CPU is running a kernel instruction, that means it's running some instructions within the kernel space of the memory. It's a reserved portion, specialized, privileged, VIP type. Okay. The other ones, the user space. If CPU is running any other program from this portion of the memory, it is said to be executing in user mode. So there are two modes: user mode, kernel mode. A CPU running in the user mode means it is running a user program, less privileged. A CPU running in the kernel mode means it is executing the kernel instructions, higher privileged. How do you decide? Well, there's a hardware support for that. There is a mode bit. It is provided by hardware. The CPU has that. If you want to switch from executing some instructions in this portion to this portion, you have to switch the privilege. Okay, please try to understand it this way. If there is a room which is for VIPs and the room for others, if you want to sit in a portion which is allocated for VIP, you have to become a VIP. You get a VIP pass and then you can enter that. That's exactly the concept. Become a privileged, then go and execute. So the CPU automatically understands, okay, this is a privileged instruction. This is non-privileged instruction. All kernel instructions are privileged instructions. Change the bit to privileged bit or kernel mode, and then you can run those. First is, it provides an ability to distinguish whether the system is running the user program or the kernel code. That's the first thing. Separate. Some instructions are designated as privileged, which can only be executed in the privileged mode or the kernel mode. And some instructions are less privileged. Now, system calls are privileged. So whenever any system call has to be executed, the first thing that happens is, let's understand. Suppose P1 has put a request to the OS to perform a write operation. Write is a system call, right? It's a sys call. Now, the first thing that happens is P1 cannot execute write. Write is a instruction which is privileged. Who will execute? Kernel will execute. How will the kernel execute? Kernel execute means the write code is here, somewhere here. This has to be executed. Okay. P1 wants to execute write, does not have the privilege to execute. Just request, please execute it for me. Puts a request to the OS. OS sees the system call and says, okay, you want me to execute the write? That means you want me to execute this piece of the code. Fine, I will. But first, CPU will be asked to change itself to privileged. How? By changing the mode bit to 1. Changes it to a privileged mode. Then CPU executes this portion of the code, which is the write instruction. That's how it is. Right? So, system calls are privileged instructions executed by the kernel. That means they reside in the kernel space. But to go into the kernel space, the privileged bit has to be set. It has to first change. Let's see how. This is the way. Let's say you have a user process and a user process was executing. Suddenly it requires to execute a system call. Very often you will be requiring that. Very often you will be requiring to execute system call. Why? Reading something from the keyboard, writing something to the monitor, reading some file, all their system calls. Whenever you want to execute a system call, the user process cannot execute. Where is the system call written? System call code written? It is in the kernel. So what happens is, it's in this way. Try to understand. This is the CPU. The CPU, I told you, there's a privileged bit. This is a mode bit. Now, this is the memory. This is the kernel code. This is the user code. So this is P1. It has an instruction which says, okay, it executes a syscall, let's say some write. But it cannot put this executing write means it puts a request to the kernel. Okay. The kernel has this code, this write code. This kernel has this write code. So this portion of the memory, the instructions written here, has to be executed. But that can only happen if the CPU mode bit gets changed to 0. It's 0. 0 is the privileged bit. It has to change to 0. How will you tell that the mode bit will be 0? Well, if you have studied in computer organization and architecture classes, the CPU, which was executing a program called P1, now has to start executing a program called the kernel code. There was some program writing here. It will stop and start executing this. It will start moving from here to here. How can the CPU be made to do so? The CPU will be made to do so by mechanism of something called interrupt. This is how things happen to a CPU. It's called interrupt. It's forced to stop the current execution and start executing something else. So every CPU has an interrupt line. Whenever a CPU gets an interrupt through that particular line, it stops the current execution and moves to the other execution. That's exactly what I need to do. I was executing P1, CPU was executing P1. Now it has to jump to the kernel code and execute the code written here. How will that happen? Well, this is through an interrupt line. This is what happens when this particular system call is generated. The moment a system call is generated, that is actually an interrupt to the CPU. This is why we call it trap. Trap is an interrupt which is non-maskable. You cannot stop it. Once there, you have to address it. That means if there is a interrupt coming through this line, this mode line, CPU has to do something. It cannot ignore that. So suppose there's a system called write has been generated by the program P1. This will actually trigger the CPU and make the mode bit equal to 0. CPU will understand, oh, it asks me to stop the current instruction. Okay, I'll stop. What does it want me to do? It wants me to jump to this portion of the memory and execute this instruction. It does that. And what is this instruction? Well, that's a kernel code. What is written in that kernel code? The write instruction. So it executes. That is what has been shown through this diagram. So the user process puts a request to the system call. The system call actually generates a trap, or we call it a software interrupt. Yes, it's called a software interrupt. Interrupt is interruption of the current execution of the process by the CPU and jump to some other process. This happens through an interrupt line, non-maskable interrupt line. This is called a trap. So you generate the software interrupt. It traps the CPU. CPU changes the mode. It becomes privileged. That means it can now execute privileged instructions. It starts executing the privileged instructions written in the kernel portion of the memory. And the system call that you wanted to execute get executed. This is what is written as execute system call. Whenever system call gets executed, finally job is done. The mode bit is returned back to 1 and you come back from this to P1 again. This is how things operate. So you allow the CPU to change between two modes, a non-privileged or a user mode to privileged or kernel mode. How? By changing a mode bit, which means instructions that can be executed in the kernel cannot be executed by the process or the user process. That is a clear isolation. User processes cannot execute instructions which the kernel can execute. If it has to do so, it has to request the OS or the kernel to execute it on its behalf. How? through system calls. The moment you execute a system call, the mode bit changes, the CPU changes from non-privileged to a privileged mode, jumps to the kernel portion of the memory, executes the instructions, reduces the privilege, and again resumes the user process. This is the concept of user mode and kernel. Is it clear to everyone how the isolation is done?
Sir, the end part, like, can you just brief it again?
Okay.
Like,
so we know that if a CPU has to stop execution of a program and jump to another program, it can be done through mechanism of interrupts. IO devices actually do it in that way. What they want to do is, this program was running, suddenly you wanted to jump to P2. How do you do that? You want, at some point of execution in P1, you generate an interrupt to the CPU, an interrupt line, and CPU stops the current execution, jumps to another execution. That is the same thing we wanted to be done here. There was a program called P1. I wanted to jump to the kernel portion of the memory and execute the instructions written there. These are called kernel code. So I wanted to switch from executing user process codes or instructions to kernel code. How? Okay. When the process was executing, suddenly it required an access of an IO. That instruction, the user process cannot execute. It is a request to the kernel to execute. Now, in addition to putting the request to the kernel, that same request for the kernel through a system call is also an interrupt to the CPU. It's called a trap. That causes the CPU to switch the mode. It becomes privileged mode. It means now it starts executing privileged instructions, which is written in the kernel. So it stops the current execution, jumps to a different part of the memory, and starts executing the code written there. What portion of the memory? Well, the portion which handles the kernel code. The kernel code instructions start executing, and that is the place where the system call code has been written. So the system call gets executed. So the rule is, whenever a user process wants to execute something that is not privileged, it generates a system call. That system call takes the CPU from a non-privileged mode to a privileged mode, or from a user mode to a kernel mode. Or we say that the CPU changes the mode, and now it can execute more privileged instructions. That is the kernel instructions. And since system calls are kernel instructions, they are executed, the results are generated and sent back to the application. This clearly isolates a user program from a kernel program. A kernel program cannot execute if a particular user program has to execute some privileged instruction, it has to become privileged and then it can execute. So there is no chance that a program, user program, can corrupt a kernel program, because it will be not given a privilege to go into that, or the CPU will be not given a privilege to execute a kernel code while being in the user space or in the user mode. It has to change the mode, only then it can execute. This ensures isolation. So what do we get as a summary? The OS has three things to do. What it does is, the three goals: abstraction, virtualization, and isolation. So abstraction ensures that all the details of the underlying hardware are hidden. The code can be reused. Virtualization ensures that all the resources, whether it is CPU or memory, can be shared among a lot of processes. Every process feels that the CPU and the memory belongs to it, but it is actually shared in a time, interleaved fashion. And isolation means it ensures that a program cannot execute special instructions. So there is no chance that kernel instructions can get executed while you are in the user code. So these are the three major goals of an operating system. Let's finish off this with the discussion about, we'll look at the code, a simple C code and we see how all the things are done by the OS, how all the three goals are satisfied. Okay, so all of you are aware of this code. It's a pseudo code, which is a C code. And as you see, there are a lot of things which are there. First of all, so it's a function. Main is a function, which is having some arguments. Okay, it's going to take some command line arguments, which is given through the argument v array, pointer to that. Interesting part is this. So there's a instruction in the code which says char buff 100. What do you expect? You expect some memory to be allocated, right? You expect some memory to be allocated. Who does that? Well, it's done by the OS. When you will be compiling, you will be allocating some space to keep some data, some array. Okay, some 100 locations you reserve, so that you will be keeping some characters within that, some 8-bit values you will be putting. So you reserve that. Fine. What else? This, you have some file to be opened. Who does that? Again, it is done by OS. What are you doing? You are actually accessing an IO. This is an IO access. Any other IO access? Here is an IO access. Okay. Fine. So you see, whether you want a file from a hard disk or you want to print something on a terminal, it's hidden. You don't need. You just use the corresponding, the system call, and you are done. Right? Then you close the disk here. You close the file. You're done with the file operation. You finish. What else? Can you identify a fault in this particular program? Can you identify anybody who can identify a fault in this particular program? Can you identify a fault? No?
The 1 minute, sir, like trying print.
Just find a fault in this program. Tell me the line which is faulty.
Sir, PTR
line
plus
number
1000?
6, sir.
6.
Absolutely. This is faulty, right? What do you expect to get? You expect to get
PTR is a character type, whereas 1000 will be an integer type.
So what is the error that you are expected to get? You're expected to get a segmentation fault. What do you mean by that? It means that you are trying to access an address which you are not supposed to. Isn't this protection? You are trying to, yes, you're trying to access a range of address which is beyond the one that is allowed for you. That's so you are ensuring isolation, not only between processes, but also between process and the OS. So you see, this is some of the code to show the usage. Okay, so we've already written that.
Sir?
Yes.
Sir, in this fixed line, how this is OS कैसे चला रहा है सर, मतलब कि ये segmentation fault कैसे हुई, समझ में नहीं आया.
So you see what I have written here in segmentation line 6. You write 1000 bytes to the allotted 100 bytes, isn't it? So what you do is, the moment you are allocating some space, suppose you have declared a pointer, and the pointer is pointing to a particular range of address locations. You have decided that can at max be PTR, can at max be 100 locations. Pointer is some address location that is pointing to those range of location. You are actually pointing to, so it's like this. PTR, what is PTR? PTR is a pointer to some 100 locations from 0 to 99. This is the pointer to the base location of this. But now you are actually trying to apply 1000 locations, and you are using PTR for that. The problem is this cannot happen, right? So the range of addresses that you had allocated initially during compilation, you are violating that. So the OS says, see, you are going beyond the one that has been allocated to you. You're not. You cannot go. That's it. Segmentation fault. What is segmentation? We'll come to that later. I'll talk about how memory can be segmented, can be divided into a number of portions, and then you allocate that segment to a particular, code. If you go beyond that, the OS will interrupt you and tell you that you are going beyond your allocated segments, and that's a fault. That's called segmentation. That's what you get when you mess up with the different pointers. What are pointers? Pointers are, address locations, the base address locations, basically. When you're trying to access any address beyond the range allocated, it says segmentation fault. That means you're going beyond the memory segment allocated to you. So this is basically the overall idea about the different goals. So I've already discussed that. There's no point in going through. I'll skip that. Yeah, so we'll end up with some examples of operating system. I'll start off with the next one just quickly. What are the examples that we have of an OS? We have operating systems for different purposes. Some are for general, work. They're called desktop, or for server machines which have high computation. So we have the normal ones: Microsoft, Windows, Unix. Unix and its different variants. Linux is that, Solaris, Mac, FreeBSD. They're all different kind of desktop and server OS. The important thing that we have in this server is resource utilization. How many programs can you run? That is most important. We want to run as many programs, run them very fast. That is the important thing. So whoever designed the OS for this desktop had given more stress on how do you accommodate more programs? How can you run more programs? So the design of OS allowed resource management and abstraction more important. Okay. Isolation is there, but okay, so resource management is very important because you allow many things to execute. In addition to that, there are other OS as well, which are called real time. Real time means some job or some program has to finish within a particular deadline. So there is a time that is associated with every program, and that is fixed. And the particular program has to end within that time. That is important, meeting the deadline. So in addition to the three goals, real-time OS also has to ensure timing constraints are met. So this is a major concept. This is the concept of real-time OS. Examples are real-time Linux, VxWorks, QNX. A portion of this called embedded Linux is used in the Android operating system. Okay, so the base of Android is Linux, embedded Linux. Then we have embedded OS. What is embedded OS? Now, embedded is resource constrained devices. Devices which do not have sufficient memory. In the, I was talking about embedded devices such as microwave oven, see those washing machines, etc. So if you think about more complex embedded devices, where you may run some 2 to 3 applications, in that case, you may require an operating system. Smartwatches, for that matter. Okay, the different gadgets that you have today, even mobile phones. What are they? The Android. You categorize that into mobile OS, but there are some specific OS for embedded platforms where the OS, in addition to the normal operation, has to take care that the resources are very small memory, not so powerful CPU, do not have a hard disk. These kind of systems are there. One example of that is Contiki. It's a very, very popular embedded OS. Even if you go to your, if you have gone to the POS machines that you have, or the purchase when you purchase something from, say, the malls, the Big Bazaar, etc., you see the OS that runs on their machines, Windows embedded. Even the one that runs in your ATM machines, the ATM counters. So they are specifically designed for handling embedded systems, that is, systems which are designed for a particular purpose and have very resource constrained power. They're called embedded OS. So this is what we have for as the introductory lecture. And yeah, so that's, let me finish off this with the design, because that is, let me quick, since I have started off, I will be taking up this. Okay, so
Sir, what are the
yes.
examples of time constraints?
Time constraints, say for example, you are running an OS that takes care of a nuclear plant, where every task that you are handling has to be finished within a particular deadline. Or let's say, let's give an example of VxWorks that was used in the Mars Pathfinder project, one that was sent to collect pictures of the Mars surface. So the rover which was roaming around on the Mars surface was a robot, and that was running an operating system. So that was a hardware, a CPU, and it was running an operating system. So in that case, it was VxWorks. So what you have in that is a lot of tasks. It has to take some images. It has to send it to the CPU, that will be processed. The particular image will be sent back to the base station, which is on Earth. And that has to happen within a certain time, or else the job will not be complete. We will take up a case study of VxWorks where you will see what went wrong in a particular situation. So these are the situations where you will be requiring to complete. There are multiple tasks like capturing images, processing images, sending it to a certain other CPU, which is somewhere else. All these are different programs. And every program has been allocated some time. The program has to finish within this time. If it is not, then it has to restart and start again. Okay, so something on this. This is why, what to do if it does not meet, that is to be handled by the OS. So we'll talk about that. Yeah, even in case of mobile phones, you want to receive some data within a particular time. That's a real-time situation. Okay, so now we shall finish off this discussion with finally a mention about the design of OS. So what goes into the OS, right? So what is there in the OS? So when I say that, okay, what do you have in the OS? Let me quickly summarize. What we have in the OS is, as you saw that the goals, now it is clear to you. What you have in the OS is a syscall interface. That's the first thing. Then we have some module that takes care of memory management, some module that takes care of CPU scheduling, some that takes care of files, that is file management, and something which takes care of the inter-process communication. So overall, obviously below that is device type. So this is what makes up an OS. Let me go one by one. At the bottom is the device driver, because here are the different devices: device 1, device 2, device 3. What somebody was asking me, isn't it? So for every device, will there be a code of access of the device? Yes, that's what we call the device driver. If you have a new device that you want to attach, that device has to be programmed. Device means the device controller has to be programmed. So the code for programming that controller should be now part of the OS or the part of the kernel. So the device drivers should be there. That is why you see I've written device driver at the bottom. They are the ones that, so this is the hardware part. So the device drivers talk to the hardware. And this is the portion which connects with the app. The app wants to use these devices. How will that happen? Apps ask interface. System call interface means the list of system calls maintained. App has to know that particular system call. It puts the request via that system call. And one of these, either the memory management or the file or the CPU or the IPC will come into play. We'll use the device driver to talk to the device, get the data, and send it to them. Suppose the app wants to use a file. It has put a request from the interface, that is from the list. It has put a request, say, called open. That's the system call it uses. So it has made you the system call interface. Open followed by the name of the file. Okay, the file management module comes into play. It looks at this string and finds out, oh, it is asking me to open a file. Where do I get the file? It looks up this string, looks up the file management /home/IITA/desktop. It looks up to this directory structure, finds out the file, goes to that particular device driver. Device driver in this case will be the hard disk controller. It goes to the hard disk controller and tells me, see, I have got this file called FOO. I want this FOO to be given to me. Well, the device driver looks up to this FOO and finds out, okay, FOO is in this particular sector of my hard disk. The device driver starts working, goes to that particular sector, collects the block, sends it to the OS. OS passes on to the file to that. That's how it works. Is this clear? How things, they're all interrelated. App puts a request via system call. You want to have one level up than system call, okay, file, you use a GUI. You type in file, open, it actually gets translated into the open system call. The open system call is passed on to the OS. OS brings in the file management unit. The file management unit requests to the hard disk device driver. Okay, device driver. The device driver in turn asks this to the hard disk controller. The hard disk controller goes to the sector of the hard disk, collects the sector, passes it on to the controller passes it on to the file management unit, the file management unit passes it on to the OS, OS passes it on to the system call, and finally to the app. And you get the entire thing done. That's what happens. Clear? If all of this feature is entirely in a kernel, if this entire thing, this part is one single kernel, you call it monolithic kernel. Monolithic. Only one block. Everything is in the kernel. Everything. It's called monolithic. Linux is a monolithic kernel. XV6 is a monolithic kernel. Everything is in the kernel. That's called monolithic. It's one way of designing. You keep everything. The problem is tomorrow you want to bring new things. You have to include it in the kernel, and the kernel keeps on becoming bulkier. That's one way. The other way is you keep only the special portion in the kernel. The kernel is only very light. It's very light. You only keep some special services in the kernel, and rest of that you keep as an applications in the user space, like file management. Okay, say memory management, not memory management, some like IPC, etc. You keep them as services. So there's an app. The app wants to use a file. It puts a request to the file kernel, to the system call. The kernel goes to the file management, gets it, and then sends it back to the app. There is transition, there is request, but it is a two-layer. The file management portion is not part of the kernel, right? It's provided as a service. So this is how you can use it. This concept is called micro kernel. All services are provided as, all this union management is provided as services, and kernel is like. Okay, so we'll talk about that later on. QNX is one example of microkernel. I'll talk about that later. So that is what we have for today. And
sir, please explain monolithic again.